Whenever. All right. Good morning, everyone. Welcome to Argonne, Distinguished AI Lecture Series. My name is Duarte. I am lead for Translational AI at the Data Science and Learning Division. And I thank you very much for joining us this morning. This series tries to create synergies with researchers within and outside the lab. And today I am very glad to have as the speaker, Javier Duarte, who's going to be presenting the talk, AI at the Edge of Particle Physics. And just for you to know a little bit about Javier, he's an assistant professor of physics at the University of California, San Diego, and he's a member of the CMS experiment at the CERN Large Hadron Collider. Before joining San Diego, he was a Letterman postdoctoral fellow at Fermilab. He received his PhD in physics at Caltech and his Bachelor of Science in Physics and Mathematics at MIT. His research interests are around Higgs boson measurements and searches for new physics at particle colliders, real-time artificial intelligence, and FPGAs, geometric deep learning for particle physics, and the convergence of all these different elements. Javier received the DOE Early Career Award for Real-Time AI in Particle Physics, and is a co-PI of the DOE project FAIR for HEP, where he is applying principles of findability, accessibility, interoperability, and reusability to AI models and data in particle physics. So Javier, we are really glad to have you with us today. Go ahead, please.
Great, thank you so much for that introduction. Hopefully I am sharing now.
Yes.
Okay, great. Great, so as LU said, I'm giving a talk today on AI at the edge of particle physics. And just as a quick teaser for something that will come up later in the lecture, actually, sorry, let me minimize this. Great. So as a teaser for something that will come up in the second part of the lecture, I just want to put something in your thought now is, what do Mars exploration and particle physics have in common? This is just a picture of the Mars 2020 Perseverance rover. So as a quick intro, something that maybe not a lot of people know, but machine learning and neural networks in particle physics isn't necessarily something new. And in fact, they've been linked to each other since the 1980s. So there was a lot of pioneering work done in the late 80s by Bruce Denby and others. And really since then, it's just flourished. And in recent years, the use of machine learning has really expanded into a lot of new territory in particle physics. So this kind of started with machine learning for the quote unquote problem of jet tagging, which is trying to identify the origin of the particle showers we see in our detectors and what kind of particles actually produce these showers. And that was sort of one of the first big revolutions, is using machine learning for this task. But since then, we've also been using machine learning to actually generate and simulate our data. Machine learning for event reconstruction, which is when we take the detector hits and signatures that we see and try to, again, infer what kinds of high-level objects that physicists know and love, like photons and what kind of particles they correspond to. And then finally, also fast machine learning for the trigger. So the real-time event filter that we use to decide which events to save and analyze and which events we essentially throw away. And so all these aspects are sort of new ways we're using machine learning. And in this talk, I'll focus on the two of these, which is machine learning for generation and simulation, as well as fast machine learning for the trigger. And broadly speaking, we're interested in two main advantages from using machine learning in these contexts. One is to improve our sensitivity to physics, so actually be able to discover new physics easier or in ways that we weren't able to do before. And also improving the computational performance of our software algorithms. So basically trying to get our algorithms to be more efficient or run faster than previously possible. Okay, so to give sort of a little context, of course, the experiment we work on, or the collider we work on, is the Large Hadron Collider located outside of Geneva, Switzerland. It's a 27-kilometer in circumference collider. So you can see here it's the spatial extent of it. It's a 13 TeV proton-proton collider. There are 4 interaction points, 4 different detectors situated along the ring. At each of these points, we have roughly 40 million collisions happening per second. And an individual collision actually isn't just a single proton hitting one other proton, but in fact, bunches of protons passing through each other. And so what that means is you get this sort of mess of many collisions happening all simultaneously. So we call this phenomenon pileup, which is when many collisions are happening at the same time. And so you can see it's a little bit more complex than maybe the simple picture of just one proton hitting one other proton. And just to give you an idea of how what kinds of events we look for, if we're looking for example, a Higgs boson, one of the more recently discovered particles at the LHC, it's actually produced only once out of every 10 billion collisions, which means that the LHC produces a Higgs boson roughly once every 4 minutes. And so this is like a very rare process. And so one of the things that we do is we first, basically, we can only analyze about 1,000 collisions per second. So we can only analyze a small fraction of the collisions that happen. And you could see in an even smaller fraction, we have rare events that we're interested in studying, like Higgs bosons. So it's a really important task. This triggers a very important task in that we need to make sure we're selecting the right events, and we're not throwing away these very rare events like Higgs boson production. And the experiment I work on is the CMS experiment. Pictured here, it's head on, and it's corresponds to the star sort of on the left of the screen. So a quick word then about the CMS detector itself. So it is pretty large, almost 3 stories tall. And it's composed of many specialized components, that each of which is designed to measure different types of particles like muons, photons, and hadrons. And in total, it corresponds to about 100 million channels of each one giving a signal that we can then analyze to try to reconstruct what happened in each collision. But very at a very high level, you can kind of think of it as a big camera that takes these detailed 3D snapshots of the collisions. And so one example of how we actually, interact, or how we actually see particles that we, often see in the detector is our quarks and gluons. So quarks and gluons are fundamental particles that interact via the strong force. So that means that they're never seen in isolation because of confinement. And so that means that they actually, when they sort of come out of the collision, they eventually become jets of hadrons, which are bound states of quarks and gluons. And by jet, I mean basically this spray of particles, of many particles that we see that get all kind of moving in the same direction and that we collect in our detector. And so as you can see here, one essentially initial quark or gluon can actually produce a spray of many charged and neutral hadrons. The charged hadrons bend in the strong magnetic field that we have in the detector and leave tracks in the tracker, and then also deposit their energy in the hadron calorimeter, which is the piece in yellow that you see there. Similarly, neutral hadrons, which don't have charge, will do a similar thing, but they don't bend in the magnetic field and they don't give you tracks. So you get these different kinds of signatures for the different kinds of particles that you might see in the detector. And then what we do is we take all of these different signatures, the tracks and the energies, and we cluster them into like one high-level object, which we call a jet, and it has this kind of characteristic cone shape. And the interesting three interesting observables that we associate to this jet are the transverse momentum, or PT. This will come up a lot. This is basically the momentum of the jet transverse to the beam direction. And the other important features are sort of where it is in the detector, which we parameterize with phi, sort of the angle in the XY plane. So we usually situate our axes so the z-axis is along the beamline. So this is asking basically in what direction is the jet going in the plane perpendicular to the jet axis, to the beam axis. And then finally, there's this ADA, or this pseudo rapidity feature, which basically tells you how forward the jet is. So if it's basically perfectly perpendicular to the beamline, that's an ADA value of 0. If it's more forward, it increases the pseudo rapidity value. Okay, so that's kind of just setting the stage in terms of what kinds of things we do at the LHC. But one of the things that is a big pressing issue is actually thinking about how we analyze these events, and especially in the context of the looming upgrade of the LHC called the high luminosity LHC. So currently, we have a large amount, we use a large number of CPUs that analyze these events that you can see on the left. This is showing you what a collision might look like in the current running conditions, or the previous running conditions at the LHC. So we have an average pileup of 40, which means there's like on average about 40 collisions happening simultaneously. But we expect that the CPU demands will increase tremendously in the next coming years once this high luminosity LHC upgrade happens, which is currently scheduled to happen sometime in 2026. And what happens is, in order to essentially increase the data that we want to analyze, and we're trying to increase it by a factor of 10. In order to increase this data, we have to actually squeeze the beams to a much smaller area. And what this means is that you have a much higher probability to get interactions. So you get many, many more interactions happening simultaneously. So on the right, it's a picture of what this increased pileup looks like. This is a pileup of 200, which is what we expect for the HL-LHC. So essentially, we expect these events to get a lot busier, a lot more complex. And at the same time, our current reconstruction algorithms will have a lot of challenges. Our current computing algorithms will have a lot of challenges with this kind of data. And so we need essentially more processing power or smarter algorithms, including using things like AI, in order to keep up with these demands. And so that's kind of setting the stage as to why we're so interested in using AI, especially to improve our computational performance. And so this is kind of the segue into part 1, where I talk about how we're using AI for generation and simulation. But maybe I can take a quick break here to see if anyone has questions on the sort of intro. Okay, maybe not. Maybe everyone knows this already, so that's great. So the main result I'll be talking about for this part of the talk is actually this paper, so particle cloud generation with message passing generative adversarial networks. So I'll explain kind of what all that means, and first kind of set up the problem that we're trying to solve. So again, we expect that there will be these hugely increased CPU demands for the high Lumi LHC. But even currently, we have these very high computing demands, and a big chunk of it has to do with the simulation, has to do with how we simulate our events in order to do analyses where we can compare different hypotheses and things like this. So at the beginning of run 2, for example, this simulation took up around 40% of the CPU resources for CMS and Atlas. And since then, things have only become more complex, requiring that the simulation will become even more of a CPU burden. So for instance, the detector upgrades for the high luminosity LHC mean that there's going to be increased complexity in the actual detectors themselves. And further technical improvements are kind of expected to be limited in how we do this simulation. And so as you can see from this kind of pie chart, the generation, simulation, and reconstruction of the simulation is expected to be a significant fraction of the future CPU load. So 27% of it will be for these tasks. So to give you an idea of what that kind of looks like, or what are these traditional simulation engines look like, we basically use, for this full simulation, we use this software called JEONT4, which explicitly models the detector geometry and the materials and the interaction with the particles. And generally for this full simulation, it's highly integrated with the experiment because it's so experiment specific. So because of that, we have very CMS and Atlas, so both have their separate full simulation workflows, although they're both based on this Geant4 modeling of the detector. Then there's fast simulation. So that's kind of a faster version, which implements approximations. So in particular, things like the shower shapes might be used, might be sampled analytically with some approximations. The reconstruction might be done with an assistance from truth information and simplifying things. And then finally, the even fastest version of this current simulation, which is not necessarily used for official experiment results, but used for more kinds of phenomenological studies or other kinds of things, is called Delphis. So this is a package which allows you to do really ultra fast simulation, but really is essentially tantamount to kind of parametrized smearing of the generator level information. So this is, again, is like kind of the fastest option, but also may be the least accurate of the three options. Okay, so what are the kind of strategies that we can imagine for using machine learning to augment or replace parts of this? So one of the strategies we might have is to kind of replace part of the full simulation. In this case, we can kind of try to imagine the goal is to try to increase the speed, but preserve the accuracy of this full simulation. Another approach, of course, might be to replace parts of fast simulation, which again, you want to maintain the speed, but potentially increase the accuracy or even increase the speed as well. Then there's an approach which I'll call this conditional approach, which is where you kind of start from a generated event, so an event before simulation and reconstruction, and then we try to basically apply algorithms that kind of figure out what the mapping between generated events and reconstructed events look like. So these kind of simplified pure particles, and then get actually what the detector signature looks like and kind of map those two things directly. And then finally, the approach that I'll kind of focus on for this talk is kind of a more end-to-end approach, which is when we, rather than relying on the existing generation or simulation workflow, we kind of do a new end-to-end one where we map this kind of random noise as the source of sort of randomness to reconstructed events directly. So this might be ultimately the fastest kind of approach, but also may not necessarily be the easiest to do all in one. So I'll kind of compare and contrast some of these approaches. So again, we're looking, the main goal we're looking at is kind of the speed versus accuracy. So we want to see if machine learning based algorithms can either achieve higher accuracy than the really simple fast simulations like Delphis, or produce faster results than the more full complex simulation like Geant4. And so we're kind of looking to see if we can move, in this accuracy speed plane towards the top right somehow, either speeding up existing algorithms or increasing the accuracy of fast algorithms. And one thing that's nice about machine learning algorithms, of course, is that they can be accelerated with dedicated coprocessors like GPUs and FPGAs, which I'll focus on a little bit more at the end of the talk. But there are challenges associated to trying to replace these existing algorithms with machine learning. So one is, of course, that these algorithms, machine learning algorithms, will need really large training data sets and a lot of training time. There's kind of questions about the statistical validity of extrapolating from the training set to larger sets if you're generating more than the training set, for instance. You might want to retrain the algorithms for changing conditions and formats. And finally, integration into existing experiment workflows is also kind of an outstanding issue, although there has been some success on the Atlas experiment, which I have a little bit on the backup on if there's some interest. But yeah, so that is one key issue, again, moving forward. Okay, so all those caveats aside, the main sort of workhorse of this kind of machine learning for simulation that has been done, a lot of pioneering work has been done already, is using generative adversarial networks. So the main idea here is you want to essentially train two networks in tandem. So one network will take random noise and generate realistic fake data from this random noise. And the other will act as a adversary. So this network will be a discriminator to try to discriminate real data from this fake data that this generator creates. And you basically train these against each other. So you train it so that the generator is, penalized whenever the discriminator is able to distinguish these two. And hopefully you basically end up with a generator that is well trained enough to at least fool the discriminator that it can't, and such that the discriminator can't tell the difference between real and fake events. So this, of course, has been popularized in throughout, I guess, the internet or throughout culture as these deep fakes. So if you go to thispersondoesnotexist.com, you can see many examples of these so-called deep fakes that are actually just generated images from this style GAN, one of these generative adversarial networks. And as you can see, these images are actually people that don't exist. They're completely, generated by this network, and they produce really realistic looking results. Okay, so that being said, that they do seem very impressive, and GANs do seem like a natural solution to this kind of generation problem. But there are some issues. So one is that because of this iterative process where you alternate training the discriminator and the generator, it's not always mathematically guaranteed to converge. And in fact, you can have a lot of stability issues in trying to train these GANs. It can be very difficult to get convergence in general. Another big issue is the phenomena of mode collapse, which is where GANs sort of start to ignore parts of the input data or features. So for instance, this is a GAN that should be outputting numbers between 0 and 9. And as you can see, it has a strong preference for the numbers 1 and 7, and maybe any other numbers that kind of look like 1 and 7. So you can see this is an example of mode collapse, where instead of generating the full phase space of possible data, they kind of focus in on certain parts of the input data. Other issues include things like vanishing gradients, where you're unable to improve the weights anymore. And standard approaches like convolutional neural networks require voxelization or feature selection for deep neural networks, for dense neural networks. And finally, even after all this, solving all these issues, the results may be imperfect. So this is just one example where you can see in the background that there is some kind of some faulty, definitely something that a human would be able to tell there's something wrong with this image. And this is just an example from clicking through that page. So nonetheless, given, again, putting these caveats aside for now, let's try to apply GANs to a classic HEP data challenge, which is generating these kinds of JETs objects. So before we can do that, we have to kind of think about how we should actually represent the JETs as a data format. And one of the things we can look to is how data has been represented in deep learning successfully. So in deep learning, so far, we've kind of thought about mapping algorithms to the structure and symmetries of the data. So having these two tied together, essentially. So for instance, convolutional neural networks work really well for images, which are these like grids of pixels, because they kind of take into account this translational invariance of the images. Similarly, recurrent neural networks, or more recently transformers, work really well for language processing because they can kind of take into account the context of each word, the context of each thing, and kind of recursively look at that. So what about high energy physics data like jets? So some of their features are that they are distributed unevenly in space, so it's not a regular grid. They might be very, very sparse. It might be only certain pixels are highlighted if you think of them as an image. And then also there's no defined order. So some kind of architecture that has this idea of permutation invariance would be preferred. So one way we can take into account all these features is actually this representation of a jet as a so-called particle cloud, or essentially a graph. So we take all of these particles that might be coming out of the collision, and we actually take each one of them and treat them as a node in an interconnected graph. And so the node features might be things like the momentum of each individual particle. You could also consider things like edge features. So these are features of pairs of particles. And this might correspond to things like the distance between particles in this eta phi space, in this special space that we use in Hadron Collider physics. And then you can also look at like kind of global observables of the jet itself. So things like the jet mass is a really critical feature that we use in a lot of analyses. And that's kind of a feature of the particle cloud in total. So you can compute it by using all of the information from the different nodes. Okay, so with all that set up, I can talk now about the actual paper in which we propose a few different things. So one is we propose a new architecture to do generation of these kinds of jets as particle clouds. But first, we actually need a data set that we can use for this kind of generation. And so the data set that we propose is called JETNET. And it's a public data set for benchmarking GANs, focusing specifically on this particle cloud representation instead of image representations. And I put my graduate student Raghav on this slide because he's very much leading this this effort, and so he's very much the leader of this work. So what this means is instead of these 2D images, we'll basically create these particle cloud representations of the data. So we only have essentially the particle information, and which could be, in fact, variable size. So it's a similar idea to this ShapeNet dataset, which actually kind of revolutionized how point cloud generation and point cloud generation was done with AI models. And our data set specifically consists of 30 particles, up to 30 particles per jet with 3 features. And so in this case, there's PT, the relative PT with respect to the jet, the relative pseudo rapidity, and the relative angle or phi angle of the particles with respect to the jet. And it consists of about 500K gluon, top quark, and light quark jets. So different kinds of jets, all with PT of around 1 tera electron volts, just for uniformity. And these were generated with MadGraph and Pythia and a very simplified detector simulation and reconstruction. It's publicly available on the Zenodo platform. And this is all kind of related to this Fair for HEP effort that Eliu mentioned at the beginning, that we're collaborating with Argonne as well as other institutions to try to basically create more fair data sets for high energy physics, of which this is definitely one that we aspire to make fair. Okay, so again, so now we have a data set. So how can we evaluate different kinds of generators? So evaluation of these generative models is in general difficult. There's not like a simple metric like accuracy that you can really say. You have to somehow like look at the data in aggregate and say, does this data look like the data that, the real data? And how does, do we see any outliers and things like this? These are difficult questions to answer. So we want to somehow evaluate quantitatively the quality of the data, the diversity of the data, so whether it actually spans the full phase space and there's no evidence of mode collapse, and ultimately the physics performance. So in this case, like how much the data matches with the real physics distributions of these observables. So to do so, we propose actually 4 physics and computer vision inspired metrics. Unfortunately, I don't have time to go into like the detail of each one of them, but suffice it to say that each one of them is basically designed to kind of measure or quantify a different aspect of this, the quality, the diversity, and the physics performance. And the ultimate measure, I think, is this 1 Wasserstein distance, which is basically looking at the distributions themselves and quantifying how similar does the distribution of our physics observable look when you look at the data that's generated versus the data that, the real data. Okay, so we actually proposed a message passing architecture. So this is a kind of a graph neural network in order to analyze these kinds of particle cloud data. So the way it works is you start with an initial particle cloud of noise. So this again is kind of the noise as input. The generator then takes these different noise inputs. So you can see there's basically these noise features, H10, H20, these are noise features of different particles, and passes them into a message passing architecture. And so the way that this works is it basically takes pairs of particles and computes a message. And then this message is sent to each of the pairs of particles to compute basically an update to the hidden state of that particle. And then that process is iterated throughout the particle cloud. And so the neural networks here are basically the two that you see here. The FE and the FN are the two different neural networks that are used inside of this message passing architecture. And so finally, after this is done, you can iterate this process as many times as you want to get a generated particle cloud. So now you have a new particle cloud that has, certain features per particle inside of the jet. And so the final features in this case might be things like the eta, phi, and the PT. And then finally, we throw that in to the discriminator, which might have a real particle cloud and generated particle cloud as input, and actually has a very similar architecture. So in this case, the discriminator basically is also a message passing neural network. And again, at the end, basically tries to distinguish whether it's a real particle cloud or a generated particle cloud. Okay, so with that architecture, we can actually apply it to this data set. And just to be able to visualize these we can make these jet images. So this is kind of showing you qualitatively how good the generator is with respect to the real data. So in this case, this real data is on the top row. And you can see that for top quark jets, there is this nice structure where there's these three prongs, these three decay products are kind of separated in space. And then for the message passing neural network, you can see it actually is able to reproduce that kind of three-pronged structure, at least, just kind of looking at some random results. And on the right, you can also see the average jet image is also pretty well produced. But in order to actually tell, how good of a network it is, we want to actually look at the quantitative results. So in this case, we'll look at, again, the actual distributions of physics observables. So on the left, this is showing you the particle PT, the particle transverse momentum. And as you can see, the real distribution is shown in red, and the distribution from our MP-GAN generator is shown in the blue dotted dashed line. And we also use other standard point cloud generators, and you can see those as well. And so the most interesting thing is that the real versus the MP-GAN actually are the most similar, and the other generators really fail to capture the physics of these distributions. And in particular, one of the interesting physics is the fact that these top quarks have these three decay products, and they're not always merged in the same jet. If they are all merged in the same jet, then you get a higher value of the mass. And so that's what this higher peak is in the relative mass at 0.15. That corresponds to when all of the decay products are merged in the same jet. On the other hand, you could have potentially only one of you can only have the W boson, for instance, merged, decay products merged, in which case you'll have a peak at this lower mass. So you have this interesting bimodal mass for the real distribution of jet mass in the middle, and only the MP-GAN is able to kind of reproduce that, whereas the other distributions have difficulty. And on the right, we also have an energy flow polynomial, which is a kind of jet substructure observable. So it's a more complex observable, but you can see that, again, we can kind of match that pretty similarly. And so what we can do is quantify the differences between these distributions, again, with this one Wasserstein score. And the main thing I want you to take away, so you don't have to read all these numbers, is that within the uncertainties, the message passing neural network is able to reproduce what the real one Wasserstein scores should be. And so this is comparing real distributions with other real distributions, just that are statistically independent. And finally, one last thing I want to highlight about this architecture is that it's very fast. So whereas a real generation might take order of 1 second per event to run MadGraph plus Pythia, and even longer if we run a realistic simulation and reconstruction step, this MP-GAN generator only takes about 36 microseconds per jet if you run it on a really beefy GPU, so this A100 GPU. So it is a really huge speed up to be able to run this kind of neural network to get this kind of generation. Okay, so to kind of summarize, this MP-GAN with particle cloud representation for HEP data outperforms existing point cloud GANs and also achieves accuracy on par with the real generation. And in general, what we do in this work is advocate for public data sets and benchmarks to more quickly improve the progress being made in this front. And And as a kind of a vision for the future, I kind of imagine that there should be multiple modes of this machine learning for simulation working in parallel. So the end-to-end approach that I've shown here is really useful for like analysis specific simulation. So when, if an analysis is just looking at jets, maybe they can apply this kind of architecture to generate more jets so that they can have a bigger data sample. But we also need to actually make progress on this kind of generic simulation that might be useful for, all kinds of different analyses. And finally, one thing that will kind of segue me into the next section is that machine learning inference can really be accelerated on dedicated coprocessors like GPUs, FPGAs, and also leveraging HPCs. And so this is really kind of the topic of the second part of the talk, which is how we are using AI at the edge in special coprocessors in really, really fast situation. So maybe I'll pause here to see. Okay, no questions. Okay. In that case, then I'll continue. The main work that I'll talk about here is there's lots of papers and lots of work summarizing this and lots of collaborators that I'd like to acknowledge. So yeah, there'll be links in the talk about accessing all these papers so you can kind of follow along. But yeah, there's lots of work and collaborators that definitely contribute to the work I'll summarize here. Okay, so the again, so there's different kinds of computing hardware alternatives that we can use for machine learning in general. So you can imagine CPUs are kind of one end of the spectrum, which have like the greatest flexibility, but also may not be the most efficient for specific tasks. Then of course there's GPUs, which have higher efficiency, but maybe less flexible. They kind of are full, again, for kind of specific use cases. And then moving a little bit closer to the efficiency side, there's field-programmable gate arrays, or FPGAs, which can be reprogrammed, so they still retain some of that flexibility, but they can also be much more efficient than other platforms. And then finally, there's ASICs, which are potentially the least flexible, but can also definitely be the most efficient because they're specialized for a specific application. And so this kind of sweet spot that we might be looking at is, and that we focus on for the LHC, especially this trigger, is our FPGAs. And the reason why we focus on this is because of the really tight latency requirements that we have in this trigger. So each collision, happens at a rate of 25 nanoseconds, or so we have this 40 megahertz collision rate coming off the detector. This first stage of the trigger, the level 1 trigger, needs to reduce this down to about 750 kilohertz. This is after the upgrade. And so because of this like really high data throughput and low latency requirements, so in general, the latency requirements about on the order of microseconds, we have to use kind of FPGAs for this system. After the system, it can go to this high level trigger, which uses CPUs, and then again reduces the rate down by another factor of 100, essentially. And then finally, this can then be analyzed offline. So again, the kind of hardware that we use differs at the different stages. So on detector, we really need ASICs because of a variety of requirements. In the level 1 trigger, we can use FPGAs, and then afterward, we can also use CPUs. So I'll focus on this part of the trigger. And so the main goal of the trigger is to reconstruct all the events and then reject 98% of them within the 12.5 microsecond budget that we have for the full trigger. So that means that individual algorithms usually have to be less than about a microsecond in latency and be able to keep up with new events that happen every 25 nanoseconds. So that means in this interval, we usually call the initiation interval. It's how long the algorithm, you have to wait before the algorithm can accept a new set of inputs. And so this, again, this latency really requires this all FPGA design, and there's many algorithms running on actually 729 FPGAs. You can see each of these different blocks corresponds to one FPGA for this full trigger system. And the individual algorithms also usually have to fit on less than one FPGA. So you usually don't have algorithms split up over multiple FPGAs. And so one of these, just to give you a picture of one of these boards, looks like this. So this is one of our upgrade boards that features a type of FPGA on it. And so then the main question is, how can we actually program these FPGAs on these boards? So right now, sort of the standard way to program these, or let's say up until recent years, the standard way to program these was to use this so-called register transfer level language. So say you wanted to program a simple function like an adder on an FPGA. So you have these two inputs, A and B, and you want to add them together. So you want to get an output that's Y equals A plus B. So you would write up this kind of RTL code that looks like this. And then this code will be synthesized into so-called gate level into these gates. So for instance, this adder might be represented by gates like this. So, these are, and, or, nor gates that all basically implement this adder function, depending on how many bits you're using. So in this case, there's 4 bits for each of the inputs. So that, tells you how complex this adder has to be. Okay, so as I said, more complex operations can be decomposed into these core operations of these gates. So essentially, we have these like kind of fundamental atomic units, these like and, or, XOR, NAND, and so on, these gates. And so we want to be able to implement these in hardware in a way that's like reconfigurable. And so one thing we can do is kind of think of them as arbitrary lookup tables or LUTs. So in this case, essentially, each of these gates you can think of as just these 2-parameter or 2-input lookup tables, which give you a pre-specified output given all the possible combinations of inputs. So we have this kind of conceptual mapping between the core operations, these gates, and these kinds of logical structures called lookup tables. And so how we can then reprogram the hardware is basically by spreading out these LUTs all throughout the fabric, all throughout the chip, together with reprogrammable interconnects. So basically, we have 2 pieces of the puzzle. One is these programmable logic blocks that can implement these arbitrary logic functions, and the other is these interconnections between them so that we can reroute basically the signals depending on where we need them to go. And so once we have these 2 ingredients, then we can basically reprogram the hardware in order to implement whatever algorithm we want. So if we want to do a 4-bit adder, we can essentially hook up the LUTs or program the right LUTs that we need, and then connect them in the right order so that we can get that same function that we want. So that's essentially how programmable hardware works. Although with the caveat that modern FPGAs are a little bit more complex than that. So there's actually now more kinds of embedded components you can have. So you have these things called DSPs, which are dedicated to perform multiplications. We still have the LUTs, which are bigger and can apply logical functions. And then we also have memories like these block RAM units that can store information. And the other big aspect that we use at the LHC is this high throughput IO. So we use order of 100 optical transceivers running at order of 15 gigabits per second in order to get all this data in, do all the processing, and then get all the data out. And so we can do this all in parallel with all these different components and still maintain relatively low power. So again, the big con for this is that it requires a lot of domain knowledge to be able to program. And so that's one of the main bottlenecks, especially for physicists. So what if instead we could specify something like an AI model, something that we want to implement in order to do our selection, our event selection for us, but then sort of just specify, hey, this kind of model would be nice, and we can like automatically get an example of an FPGA algorithm that we could then implement. So how could we kind of go about doing this? Well, this is exactly the kind of goal of this project called HLS for ML, which is a co-design tool for scientists or machine learning experts to translate their machine learning algorithms into RTL firmware. So the way that it works is basically there's kind of the standard machine learning design loop which might involve like optimizing a model and then kind of iterating on that and potentially compressing it in different ways, which I'll discuss in a bit. Then HLS for ML can actually convert this to a so-called high-level synthesis project, which is a kind of different way of writing firmware, which looks a lot more like C++ and makes it a lot more kind of understandable to physicists. And from at this stage, you can actually tune the configuration. So depending on your ultimate application. And then finally, from there, you can actually export it to different kinds of designs, depending on which FPGA or which kind of hardware you're targeting. And in fact, we even have some support for ASICs through this Mentor Catapult HLS system. So to give an idea of what kinds of things you can do with this HLS for ML, I'll just talk about one benchmark algorithm, which will give you an idea of what kind of knobs you can tune. So this is a small multi-layer perceptron, which is just tags different kinds of jets as in their origin. So you can see this is basically trying to tag these 5 different classes of jets using this fully connected neural network. And it is able to correctly identify the particles about 70 to 80% of the time. And so this will give us a good baseline to compare how we can implement this on an FPGA. And so we can kind of zoom in on what the actual operations are of the neural network. And so you can see there's basically 3 basic kind of atomic operations that happen. One is the multiplications that happen between the weights and the input. The weights and the inputs. The other is the addition of potentially of a bias term. And then the third is basically this application of this activation function, some nonlinear activation function, which might be like a sigmoid or a ReLU function. And all of these different aspects can actually map nicely onto the FPGA resources. So you can use like DSPs for the multiplications, lookup tables for the addition and the activation functions. Okay, so that being said, then the question is, how much does this scale to really, really large neural networks? And actually, this neural network isn't even that large, but can still give us a good baseline for comparing. So in this case, we have about 4,256 multiplications that we need to do. So the question is like, can we compress this model and still achieve the same accuracy? And in general, this can be done with this process called CODESIGN, which is the kind of intrinsic development loop between the algorithm design and the training and the implementation. So you kind of are working both on the model side and the implementation side to make the model better. Sorry, my slides are frozen. Okay, great. So the first aspect of CODESIGN is compression. So that's where we try to maintain the high performance while we're pruning away connections that are not needed. Another aspect that we can use is called quantization. And this is where we reduce the precision from 32-bit floating point to maybe 8-bit integer or even lower in order to, again, reduce the number of operations that need to happen in the hardware. And then finally, another aspect that we can control is the parallelization, which is how fast we get the answer versus how many resources are needed. So basically, how many copies of the algorithm we need because in order to like parallelize things faster. Okay, so to show kind of some results, so here we can take our original model that we used here, and we can actually train it in a way that the training process is aware of the quantization we'll use. So instead of 32-bit floating point, it turns out that we can get actually full performance with 6-bit fixed point. So you can see this is showing you basically the ratio of the model accuracy on the FPGA divided by the accuracy in the CPU. And we can actually get all the way down to 6 bits and still maintain essentially the full accuracy that is used in the CPU. And with that, we actually get a much smaller fraction of the resources. So you can see that originally, whereas we might need to use like 16 bits without this quantization-aware training, and the DSPs might be something like 50% of the chip, we can now get down to using almost a negligible fraction of the DSPs, and it comfortably fits on one FPGA. So another aspect that we can tune is the parallelization. And so that's essentially how much we want to reuse the resources. So decreasing the reuse factor, this is this parameter that we use that controls how much we are reusing resources, increases the parallelization and decreases the latency. So for instance, we can take, if we initially use like a reuse factor of 6 for this model, that might correspond to a latency of about 175 nanoseconds. If we decrease the reuse factor and try to parallelize fully, we can get down to 75 nanosecond inference for this neural network. So really comfortably fits within the latency requirements of less than 1 microsecond. Okay, so I wanted to share briefly 3 applications of HLS for ML, recent applications. So one is actually in CMS, and the goal here is to measure the MUON transverse momentum in the ENDCAP based on information available in the level 1 trigger. And there are challenges associated with this because there's a non-uniform magnetic field with little bending. There's large background from multiple sources. We also need to incorporate new MUON detectors that have very different technology and somehow incorporate all this information. And we basically want to maintain the same trigger threshold, even though we're going to be going to higher pileup in this upgrade. So in order to do this, we basically train a neural network to regress the MUON transverse momentum based on 36 inputs from these different MUON detectors. And what we find is a factor of 3 reduction in the trigger rate using this neural network over the previous approach. Moreover, it's actually much more linear or much more stable with respect to pileup. So even if we increase the pileup beyond where we expect it to be, this algorithm will still work pretty well. And it also fits in the trigger latency requirements. So in this case, this algorithm takes about 240 nanoseconds, and the FPGA resource requirements are also met. So it's less than 30% of the FPGA, also including other aspects that they're running at the same time. So this is one example of this in the CMS technical design report for the upgrade. So another aspect that we want to consider using HLS for ML for is actually compressing the data from the detector. So one of the new detectors at CMS is called the high granularity calorimeter, or HGCal, and it is much more granular than previous detectors. So the amount of data that is produced by it is just like orders of magnitude larger than previous detectors. And so what we need is a way to sort of compress that data before we send it off the detector. And so what we're using is a machine learning algorithm called an autoencoder to basically do this data compression. But there's additional requirements, which means we can't use an FPGA here. We actually have to use an ASIC because of the radiation tolerance requirements, as well as the low power requirements for something to run on the detector. And so in this case, we use this autoencoder architecture to and implemented it on an ASIC. And in fact, it's reconfigurable, which means that the weights can be changed, even though the ASIC normally is this fixed design. And the idea is that these weights can be updated anytime the LHC conditions evolve, or perhaps there's a new training of the autoencoder, or we want to improve detector, for example, if we want to improve the detector performance. And so what this looks like is shown here. And essentially the interesting facts of it are that the latency is 50 nanoseconds, so it's pretty fast. And the power usage, or rather I should say the energy per inference, is 1.2 nanojoules, and the power is 48 milliwatts, which is because of the rate, the high 40 megahertz rate that it needs to be run at. But yeah, so this is one really interesting application for data compression on the detector. And finally, just as a final example, we're also looking at applying anomaly detection algorithms at 40 megahertz in order to basically select data that looks different from our usual data to see if we can discover new physics this way. So one of the things that we use are convolutional neural networks as the basis for variational autoencoders. And we typically do this offline where we don't have these strict requirements. But this work led by these Katya and Emma, CERN fellow and master student at CERN, as well as Maurizio Pierini's group at CERN, is really interesting because one, you can design a neural network, a variational autoencoder that works on a variety of signatures. So I'm showing here one example of a charged Higgs decaying to a neutrino and a tau, and showing that it actually does a really good job at discriminating the signal from background, even though it wasn't trained for the signal. But moreover, actually, you can actually implement this on the FPGA for a small fraction of the FPGA resources, and with a latency that's less than a microsecond. So you can actually fit this in, for example, the latency and resource requirements for the high Lumini LHC. So this is kind of an exciting new paper. This is hot off the press. This was just posted on arXiv last week. So you can browse that at your leisure.
Javier,
So I've talked a lot about Collider.
Sorry to interrupt you. Maybe just to alert you that we are getting close to the top of the hour. So if you want to leave a couple of minutes for questions.
Okay, yes, sure. So maybe I'll just summarize here. So basically there's more science use cases, but beyond those that I talked about, I focused a lot on LHC, but actually there's many others. There's also has a nice interplay with the tiny machine learning, which is a slightly different application of these kinds of ideas, but is also relevant to the kind of work we're doing. But okay, to summarize, there's intriguing mysteries related to dark matter, matter-antimatter asymmetry, new heavy particles, Higgs self-interaction, and so on that may be answerable by the HLLHC. But in order to accomplish these physics goals, we need to tackle these extreme computing and trigger challenges. And so generative AI can be used for simulation and may help alleviate some of these computing demands. Moreover, real-time AI can be used to improve the performance of our detectors, as well as save potentially overlooked data. And HLS4ML is one open source toolkit for translating machine learning algorithms into hardware for science that is in open development. These are kind of early days towards complex triggers and smart sensors and autonomous detectors. So to kind of end with the answer to the question, what do Mars exploration and particles have in common? Both essentially have to process and make decisions at the edge, which is where the sensors are, because there's not enough time really to send data back from Mars to the Earth and process it, make a decision, send it back. So processing decision has to happen at the edge. And they're both exploring the edge of the unknown. And as a shameless plug, if any of this sounds interesting to you, we're hiring a postdoc to work on this, all these things. So the deadline is September 8th, but the search will continue until the position's filled. So definitely tell your students about it.
All right, thank you very much, Javier. Let's give a hand to the speaker. It is a very exciting field of research where many different disciplines are converging to produce some really exciting results. So if you have any questions, anyone?
Hello, this is Kazutomoyoshi. So I have tons of questions, but probably we don't have lots of time. And the many of my colleagues not kind of joining this call. And is it possible to kind of maybe exchange email kind of stuff later on? Does that sound good for you?
Yeah, definitely. Sorry for going over. I'm available by email. I'll just type it in the chat if anyone has questions that we're not going to get to today.
Okay, that's good. Yeah, that's nice.
And just for your information, this presentation will be recorded in the website where we have the list of speakers. So you can share it with anyone else who could not attend today's presentation. Any other question?
I have a question.
Go
my
ahead.
question is, was there an exploration of graph neural networks considering the point cloud structure of the jet?
Yes, definitely. So the architecture that we use, this message passing neural network, is a form of graph neural network. So we tested essentially all the ones that we tested are forms of graph neural networks. So yeah, that is definitely the main type of architecture I think we're using for this kind of data structure.
Thank you. And one last question. Is it hard to convert a PyTorch code like in an inference setting to hardware using HLS for ML? Do you have experience actually doing that?
Yes, that is less well supported than using Keras, but it is we actually have active development on that front to improve that conversion. So I would say it's forthcoming to be made easier soon.
Thank you. Great talk.
Yeah.
One final question. So Javier, if you were to lay out the grand vision for all these activities, where would you like to be 3 years from now? What would be the first fruits of this international effort?
Yeah, it's a great question. I think so. For part one, I think having these kinds of tools available to all of high energy physics. So being able to use generative AI to generate additional event samples, simulate additional event samples for your analysis, I think would be really exciting tool to have. So both for Atlas, CMS, for all the other experiments as well. And for the trigger work, I think having these being used in the experiments. So having trigger algorithms that are using machine learning and being run at 40 megahertz, I think that'll be the most exciting thing. Is because hopefully by improving our trigger decisions, we might be able to kind of go beyond the luminosity limit, in the sense of it could be that we're missing out on the new physics because we're not necessarily selecting the right events. So this is like a way to actually select events in a new way that might give us access to the new physics that we've been missing.
And this is the grand vision. I actually hope to see it. Thank you very much for being with us, Javier. This is really exciting research, and hopefully at some point in the future we will see you in person at the lab, and we can continue conversations with a broad set of folks that are interested in your work.
Great, thank you so much.
All right, see you soon.